Good morning and welcome to our booth 1-4. My name is Carsten Franke from ProStep company, and I have the pleasure to introduce you to the booth and to the two posters we have there. So, the scope of the booth is architecture, common title. And the first poster focuses on integrative simulation architecture, where the need for a modular and a flexible architecture comes from, and how this can be satisfied by a comprehensive method. A second poster, be subject to the next session here on that booth at 10 o'clock. It addresses the simulation platform architecture, which is a major part of the overall architecture. The poster A is mainly divided into 5 sections, as there are the complexity and the challenges that drive us to the architecture work, the MBSE, model-based systems engineering-based approach for solving these challenges, an overview of the architecture levels that we identified, the architecture levels of the overall simulation system, the tool support that is appropriate for the model-based engineering of the overall simulation system, and finally, the benefits that come from using standards. We consider simulation as such as one overall system. Why? Okay, we have the simulated vehicle in its environment with all its components. We have the simulation core, we have simulation tasks. And so we see that the complete overall simulation system consists of entities of many different characters, with many different relations between them, let it be the vehicle internal connections between the components like the sensors and the driving function and the actuators, the connection between the simulated vehicle and its environment, houses, roads, trees, whatever, the complete model vehicle in environment connected to the simulated software. The simulation system has to fulfill, of course, a simulation task, because we do it not for hobby. And the simulation task executed on a simulation system has to follow a simulation process in order to get some credible result in the end. So managing this big bunch of different items, co-working with this, is not trivial. But we need to do it in a consistent and efficient way, of course. And moreover, each of these entities and relation, they have their own life cycles. So we have on, let's say, the functional architecture level, cycle times of some years, whereas on the most deep concrete level, changes can happen within minutes. So how do we address this? We thought, okay, this is a system. Let's take a model-based systems engineering approach to solve these complex challenges. One pattern for MBSE is RFLP. So you divide your topic by requirements, the functional, the logical, and the physical architecture. Requirements are a complete different story, so we take them apart and start with the functional architecture. We have the logical, and instead of physical, we say a concrete architecture, because, well, simulated car is not really physical. This we arranged in a matrix scheme, so we have one row for each of these architectural levels. And we have columns for each domain. Let it be the traffic participant with its subdomains. This kind of separation is not shown here, but in the final overall architecture is, of course, represented. We have the environment together. This forms simulation model. We have to have a core which executes the model, and we have to have observers which extract or distill the values, KPIs, whatever, that we need in the end for the evaluation of the traffic participant or whatever the system under test might be, its performance. So this all together forms a simulation system, needs to be executed. This is controlled by a simulation platform, which is the topic of the following presentation of the poster B. We have a simulation task, which can be subdivided. We have the simulation process. If you think about the credible simulation process, for instance, this would be subdivided into 7 columns each, according to the phases of the credible simulation process. What benefits do we get from this matrix? First of all, we get the signal flows or information flow, data flow corresponding to each of the levels. We can check this for completeness. We can, on each and every level, check whether there are gaps in the definition and, of course, close them. And this guarantees then that we have the information continuity on each level, and we get matching interfaces by design. Next is traceability. We have a vertical traceability, so we can say for each model, for each component of the actual simulation, where does it come from? Yeah, it has to have a specification, and part of the specification is a logical architecture. Logical architecture, in turn, is derived from the functional architecture, and we have again the links here. The horizontal traceability, it addresses the gapless flow of data within each level, and is subject to the process, to the concrete process. That's why we have a little icon here in the lower right corner. By this, we can reduce sources of error because we have this overview, and we can match in the end the credible simulation process, because when we start with a credible functional architecture and we have some credible process step, we can derive a credible logical architecture. And again, from this we can derive a credible concrete architecture, which makes a credible specification. And in the end, this is necessary to have credible simulation result in the end. So that's the credibility aspect. Each field of this matrix contains a management part of the overall problem or of the overall architecture. So this helps us to focus discussions. We can frame discussions usually within one field, which prevents misunderstandings, and it yields efficiency because, well, you have some structure in your discussion, and it gives a good map of the jungle where we're acting in. If we follow line by line in the inside of the matrix, we get a complete list of interfaces. So we can take this as an input to planning actions. Say, okay, we need this amount of interface, another amount we probably have already, and we can plan how many engineers do we need and how long they will take for this. Traceability is preserved following this matrix. So in the end, we get a good impact, a good benefit for the reliability and the credibility of the simulation. So now you would probably not make this on a piece of paper. The system, the overall simulation system, is big. is complex. It has a lot of details. I will not zoom in here. I just can say we can start here on the level of real objects, like the real vehicle, the real pedestrians, real streets, trees, construction sites, signs announcing construction sites, the weather. And next step would then be creating models of this real objects, functional models, because we are interested in what do they do and how do they interact. Here's a small icon taken from the Safety First for Automated Driving paper. In that paper, the functional architecture of the real vehicle is described, how the autonomous car is divided in the different types of sensors and the driving function, the actuators. And our approach is consistent with this. So we took this as one input. But of course, if I have an architecture for the car, I do not have an architecture for the environment, nor for the core, simulation core, nor for the observers, etc. So there was a lot more to add to the complete system as just the Safety First for Automated Driving paper contains. So what do we do from each level of the architecture to the next? We take decisions. Yeah? The first decision is what aspects of reality are worth to be described. The next is, okay, now I know what is important. How do I discretize this? What are the physical models for this? So like differential equations. And then I ask, how are they going to be discretized? This is actually already this fourth level from the top. And then when I have an idea how to discretize things, I need to, this is a level where the core and the observers, etc., come into the game. And then the next level would then be a logical level, which could also be subdivided in an upper logical level where we say, okay, for this and that function, what components do I need? Frequently, for one function, you need to have several components, like, let's say, anti-blocking system. You have to have the control system. You have to have the brake actuators, etc. You have to have the sensors, and all together are necessary for one function, and vice versa. Sometimes several functions can be implemented by one component. So this these are really important decisions, and mistakes can become dangerous or expensive. Then the next level is, okay, I know which components I have, and now let's consider what should be the technique to implement this. Do I use OSI interfaces, etc.? This would then the last but first level, and then the final level is the components on the concrete level, which are camera models or whatever. So by this kind of work, we automatically document all the relevant and important decisions, and they can be reused. So I do not need to consider, let's say, discretization questions again and again, just when I change some camera model. So we get the maximum reuse by this approach. In the end, we are able to even extract SSP files. We'll explain later what it is from the concrete level, and can feed these SSP files then into the simulation software. This is just a principal map. A bigger overview is shown here. You have to have this in a. You have to have a tool for modeling architecture of this complexity, just due to the sheer size of the model. You can't do it on a piece of paper, as I said. And by use of this tool, it supports you by automatically propagating changes from one item to another. So if you say, if you detect in one diagram there's something missing, there's some discrepancy, you change it there, and the system cares for carrying over this change to all the other occurrences of that component in other diagrams. So the tool is quite essential for keeping the overall consistency of the model. The next point here. And of course, it helps you and it keeps away some teachers' work and error sources by these automatisms. Such kind of a graphical table of contents is then more or less easy and straightforward to create. And this offers the opportunity to those people who are experts in one area but not in the other. You can just go here and double click on one of the boxes and then get directly to the information they need for their next steps of work. System structure and parameterization, SSP, as I mentioned, is important standard. This is Modelica hosted and it's used to define the parameterization of component models which need to be assembled and their connections. So, and it assumes that the components are given as FMUs. And with the SSP generated from our architecture directly, we can use this, import and use this in simulation tools like an OpenPath, etc. So it's a big step in the direction of automated model assembly. This leads us to the final slide, almost final slide, standards. We have a lot of standards used here in the project for different reasons, mainly the easily interchangeability of components. So let it be that you want to check different mounting position of cameras, different scenarios, a different number of pedestrians. Let it be that you want to use different ray tracer, different observers, maybe even different simulation cores, or in a situation that you are in a cooperation of different companies, or maybe even in a big company, different sites, different locations. It's good to have these standards at hand for the smooth exchange of the data. Other application is that you say, okay, for first consideration, a RAS, but cheap to execute model is sufficient. And later you say, okay, I need to improve the fidelity of the model. I exchange the coarse model, the RAS model, by a more detailed one, which is then in turn slower and more expensive for the execution. So the standards provide the necessary basis for this kind of interchangeability of components. And within the project, we have shown where these existing standards are well suited, different at many situations. However, we also detected positions where the standards need to be further developed or extended, especially when you consider the OSI standard. The project was long enough to see several releases of OSI, and let's say in the second half of the project, you could already benefit from the results of the first half of the project, because the improvements have made their path into the official distribution. So now the final slide. We are through for the simulation system architecture. As announced, at 10 o'clock there's going to be the presentation of the poster B with the platform architecture. Now I'm looking forward to your questions and answers and try to answer this.